Welcome everyone. Today we want to study geometric distribution and also we will do coding in Python. This geometric distribution is a kind of discrete probability that models the number of trials needed for first success in independent Bernoulli trials. So in today's lecture, we will go for definitions, properties, mathematical formulation, and also we will see several examples with Python coding. So once again, geometric distribution models the number of trials x until the first success, and it is in a set of the Bernoulli distribution where we have success or failure or 1 or 0, and they are independent. We have some conditions here, a phenomenon that has a series of trials, and each trial has only two possible outcomes, success or failure, and the probability of success is the same for each trial, and that is p. The geometric distribution describes the number of trials like x until the first success occurs in a series of independent Bernoulli trials, and each with the success probability of p. There are two common definitions. One, they say number of trials until first success. It means include the success. And the second one says number of failures before first success, and the success is excluded. We will use the first definition here as it is more common in many contexts. So what are the applications? Number of coin flips until the first heads, or you can say number of website visits until the first purchase, or you can say number of attempts until a machine works correctly, and many other examples in the same context. So let's go for the parameters. In here, the distribution is defined by only one parameter, and that is p. So this is probability of success, and this is something between 0 and 1. Then we go for probability mass function. For the geometric distributions, as we say, trials until first success, the PMF of a random variable like x is px is equal to k, 1 minus p, probability of failure, in power of k minus 1, multiply probability of success. So in here, k is the number of trial until first success, like 1, 2, 3, 4, and so on. 1 minus p in power of k minus 1, this is probability of k minus 1 failure, and this p is probability of success on the kth trial. So let's see one example here. For example, if we roll a die until you get a 6, probability is 1 by 6. If we get in the first, so px is equal to 1 is 1 minus 1 by 6, it is 5 by 6 in power of 1 minus 1, and multiply 1 by 6, which is 1 by 6, and then it is 0.1667. And then if it is px is equal to 2, the same 1 minus 6, this time 2 minus 1, multiply 1 by 6, and which is approximately 0.1389. Then we can go for the expected value or mean for geometry. The expected number of trials until the first success, simply ex is equal to 1 by p. This makes sense. If success is rare, you can say a small p, it takes more trial on average. Then variance is simply var x 1 minus p divided by p square. The spread increases as p decreases, reflecting greater uncertainty with rarer success. The geometric distribution is considered as memoryless. It means the probability of success in future trials does not depend on past failures. And mathematically, we can write probability of x greater than s plus t given x greater than s is equal to p x greater than t. It means it is memoryless. X follows a geometric and with the probability of p. We say x follows geometric distribution with the probability of p. And we can say probability of x greater than k is equal to 1 minus p in power of k. This property is unique among discrete distributions and mirrors the exponential distribution in continuous setting that we will study later. The geometric distribution arises from repeated Bernoulli trials. If each trial has success probability of p and failure probability of 1 minus p, then x counts the trials until the first one appears in a sequence of zeros and 1. Then we go for cumulative distribution function or CDF for geometric distribution. So we can write it as fx is equal to px less than or equal to x is equal to 1 minus p in power of x. So this fx here, this represents the cumulative distribution function, which gives the probability that the random variable x takes on a value less than or equal to x. Then we say here px less than or equal to x. This is the probability that the geometric random variable like x is less than or equal to a specific value of x. Then here we have p. This is the probability of success on each trial. 1 minus p is probability of failure on each trial. 1 minus p in power of x. This term represents the probability of having x failures before the first success. And this all together gives the probability of achieving at least one success by the xth trial. For example, here, if the probability of success is equal to 30%, then f1 is 1 minus 0.3 in power of 1, which is 30%. For the second trial, it will be 51%, right? So it means this is the getting success in the first trial, this is the getting the success in the second trial, and so on. Okay, so here we will start coding of geometric distribution in Python. To do that, first we will import NumPy and Matplotlib. Import NumPy as np and import matplotlib.pyplot as plt. Then we will define our parameters. For example, we have three values as the list of success parameters. We call them as p-values. And the first one is 30%, second one is 60%, and third one is 90%, right? So then we will have some trials. We can say number of trials from 1 to 10, right? Okay, values equal to NPA range, and in here we go from 1 to 11, so it will be 1 to 10. Then we want to plot it, right? So because we have three probabilities, we will have three plots. So we go for fig and axis, and in here we say plt.subplots, and we have one row, three columns. So in one row we have three plots. Then say, for example, fig size 15 and 5 and Sherry true. This Sherry is to share the y-axis. Okay, this is the three plot that we have made. Now we loop through each probability and plot it. So for I and P in enumerates of P values, then we calculate geometric probability based on the equation we had. The equation was something like this. Px is equal to k is 1 minus p in power of k minus 1, and this one multiply p. So we will do the same here. We can say probability is equal to 1 minus p in power of k values minus 1 multiply p. Okay, then we can go for axis I, and we go for stem plot. So we get the k values and also probabilities. Then and this is okay, let's be the same. Let's see what happened here. So you can see geometric distribution for 0.3, 0.6, and zero point 0.9, right? You can see this is the geometric probability. Also, if you want to see the probabilities, we can print probabilities here, print probabilities as well. So you can see here different probabilities has been printed. This is plotting geometric distribution. P is equal to 0.3, right? 30% chance of success per trial. Then also we need to set a random seed for reproducibility. np dot random dot seed, and in here we go for 42. Then number of samples, for example, we have 1000 samples, 1000 samples, and then we generate geometric random samples. It means trial until first success. For this one, we need to import geom from scipy. From scipy.stats, import geom. And then here we can say data is equal to geom.random variables. And in here we will pass p and size is n samples, right? So this is our data. We can print our data. So this is our data, right? Number of attempts until the first success. So we can calculate the mean of our data. So we can say mean is equal to np dot mean of data. And we can print it like print f mean sample mean is equal to like mean and 2f print, okay, 3.26. We can go for variance in the same way. Variance is equal to np dot var of our data, and we can print this one as well, sample variance, and it is 7.3. You can go for theoretical. So this was simulated mean, right? So we can go for theoretical mean. So print, we can say print f theoretical mean based on the equation 1 divided by p, right? So it is 3.33, but it is 3.26. And for the theoretical variance, we can say f, and in here we can say theoretical variance is equal to, this is 1 minus p power of, so 1 minus p and divided by p square, right? It is 7.778, and in simulation was 7.3. So this is a simulated geometric distribution, and in here we model the number of trials that are needed to achieve the first success in a sequence of independent Bernoulli trials, and the probability was something like 30%. So we generated 1000 random samples from this distribution, and we calculated mean and variance. Next, we can plot the histogram of simulated data. So for that one, we can go plot figure, and size is equal to 8 and 6. Then we go histogram data, bins is equal to range of 1, max data plus 1, edge color black, alpha transparency 8, and density true, and label simulated. Then for the x values, we can say x is equal to np, a range of 1 and max of data plus 1. Then we go for PMF. So PMF is geom.pmf of x and p, right? The rest is just about data. And also we can add theoretical PMF. So for theoretical PMF, we can say like plt dot plot x and PMF, and then here we go for red and dash line and label it as theoretical PMF. Okay, so we added title here, geometric distribution for P. We added some label for X, number of trials, for Y, probability. We add legend and we add grid here. So this blue one is the simulated and red one is theoretical. So this plot is simply the geometric probability distribution with a success probability of 30%. So on x-axis, we have the number of independent Bernoulli trials, and each one has the success probability of 30%, and with 30% chance we need to achieve the first success. Then on y we have the probability of the first success occurring on the kth trial. Then we have generated 1000 experiments, and we count the number of trials until the first success in each experiment. Also, we have here theoretical PMF. This plot the exact probability from geometric based on the PMF equation. Next, we will plot the CDF. So here we can go for count occurrence of each k. It means 1 to max k, right? So our max k was 10, right? So we can say max k is equal to 10. Then we can say, for example, unique and counts equal to np dot unique, and in here we get data and return counts is equal to true. This np unique returns two array unique which contains the distinct value in data in sorted way, and also counts which contain the number of times each unique value appears. We need to calculate the frequency. Frequency is equal to np dot zeros max k. Then later we will update it. So in here, we created the numpy array and we call it as frequency, and length is max k. At the first, they are 0. Later, we will update it, right? Then for k and count in zip of unique and count that we have received from the unique function, unique and counts. Then here, if k is less than or equal to max k, then frequency, because Python uses zero-based indexing, we can go for 1. We can say frequency of k minus 1 is equal to count. Okay. Then k values equal to np a range of 1 and max k plus 1. This is an array of k values 1 to up to max k. CDF is equal to geom.cdf, and we get k values and p. So this is okay, k values. All right, so now we can plot the CDF. So plt.figure, and fixed size is like 8 and 6. We go for a step plot, and in here first we sort our data. Then we go for npa range of 1 to n samples plus 1 divided by n. Then where see some parameters for the step plot, and label is equal to simulated CDF, and color is also equal to blue. Okay, so this is our CDF. So in here, we sorted our data. We make a range of 1 up to n sample plus 1 divided by n sample. Then where is equal to post. This is in a step function specify that the step occurs after each x value. It means the y value of like CDF that we have remains constant until the next value, sorted trial count, then jumps to a new value of y, and we label as simulated CDF, and color is equal to blue. Then we can also plot the theoretical CDF, plt.plot, and from here we pass k values and CDF and R O dash for style label. We can say theoretical CDF, and also we can define marker size as 5, right? So here you can see the difference between theoretical CDF and also so let me add legend here. We can easily understand. Okay, so the blue one is simulated CDF and the red one is theoretical CDF. We compare this CDF of a geometric distribution with a success of 30% based on 1000 simulation and maximum of 10 trials. And this blue step line represents the empirical CDF from the simulated data. It shows the fraction of simulations where the first success occurs by trial K. And this red color represents the theoretical CDF based on the equation that we have 1 minus p in power of k. The simulated CDF derived from the sorting the simulated trial count closely tracks the theoretical CDF, where raises quickly in point 0.3 at k is equal to 1 and 0.51 as k is equal to 2 here, and at 0.97 here where k is equal to 10. This is showing how the geometric distribution models the number of trials until the first success and confirming the simulation aligned with the theoretical expectation. We can also plot PMF for different p-values, like p-values equals to, for example, zero point 0.2, zero point 0.5, and zero point 0.8. Then we generate, up to 10, a range up to 10. So x is equal to NPA range of 1 to 11. Then we can say plt.figure fig size is equal to 10 and 6. Then for p in p values, then we calculate PMF. PMF is equal to geom.pmf of x and p. Then we will plot PLT, plot x and PMF, and we go for O and dash, and label will be equal to F. P is equal to P, and marker size is equal to 8. Okay, so here we go. If we add legend also, plt dot legend, we can see here this is probability of 20%. You can see here this is the probability of 20%, probability of 50%. So at the first time with the probability of 20% we get first success. This is with the 50% and this is with the 80%. So this is PMF with different probabilities. Okay, so this lecture was about geometric distribution. In this lecture, we studied the definition of geometric distribution, properties, mathematical formulation, PMF, CDF, mean, variance. Also, we see some examples and we did practical example with Python code. Please practice and feel free to ask me if you have any question by leaving a comment below this video. Thank you and see you in the next lecture.